All right, everyone, welcome back to the deep dive.
Yes, welcome back.
Today we're talking about something that I think is pretty fascinating. It's this idea of like, okay, so you've got these AI models, right?
Mm-hmm.
And these models, they're often really, really big.
Oh, yeah. Huge.
Massive, right? So how do you
get them to run on like a normal person's computer?
Yeah, exactly.
That's a big problem, right?
So there's this whole process that people have been working on, and it's called quantization.
Right.
And it's all about like compressing these models.
Shrinking them down, yeah.
Shrinking them down so they can fit and run on your laptop.
Exactly. Or even your phone, potentially.
Yeah. But what's crazy is what if someone should like sneak in something bad into that process?
Ooh, that's a good question.
It's like a trapdoor almost. Right?
Yeah, it's like waiting for you to compress it and then boom, something bad happens.
Yeah.
Yeah.
And that's actually what we're going to be talking about today.
This is real. This is not just like a hypothetical. There's a research paper that came out recently that is all about this new vulnerability and how it works and what it means.
So hit that subscribe button if you're interested in this kind of stuff, because we're going to be digging into all of that.
Go deep.
Okay, so let's set the stage right. We've got these large language models, LLMs.
The big brains.
The big brains, everyone's talking about them.
Right.
But they're huge and they need a lot of power to run.
Yeah, you need like a server farm sometime.
Exactly.
Yeah.
So quantization comes in as this technique to make them smaller.
More efficient.
More efficient so more people can use them.
The democratizing AI. That's what they call it sometimes.
I like that. Yeah, democratizing AI.
Spreading it out.
But as we've hinted at, this process might also be opening up a whole new can of worms when it comes to security.
Yeah, we're talking potential for misuse for attacks that we haven't even thought of before.
Exactly. So in this deep dive, we're going to break down how this vulnerability works, what kinds of attacks are possible, and what we can potentially do about it.
Like, what are the defenses? What can we do to protect ourselves?
Yeah. So our main source for this is this really interesting research paper. And the way they went about this is actually pretty clever.
Oh, yeah. They got creative.
Yeah. So imagine you're like a chef, right?
Okay. I like where this is going.
You've got all these ingredients and you're putting together a recipe. And one of the ingredients looks totally normal, tastes normal.
Right.
But then you cook it, you bake it, whatever.
It turns into something else.
It turns into something bad, yeah.
Like a Jekyll and Hyde ingredient.
Exactly. So that's what these researchers did. They took these existing AI models, made some subtle tweaks, and then they put them through this quantization process.
The cooking process.
The cooking process, yeah. And what they found is kind of scary.
They found that they could basically poison the model in a way that only gets activated after you quantize it.
It's like a sleeper agent.
Exactly. It's just waiting there dormant until someone tries to make it smaller and faster.
Okay, so let's back up for a second and really explain what LLM quantization is for those who might not be familiar.
Right. So at its core, quantization is all about taking those billions of weights that make up an AI model and representing them with fewer bits.
Like simplifying the math behind it.
Yeah, exactly.
Yeah.
It's like if you had a really precise measurement, like, 3.14159265, and you round it off to just 3.14.
You're saving space, but you're still getting pretty close to the original value.
Exactly. And when you're dealing with billions of these weights, that little bit of rounding can add up to huge savings in terms of memory and processing power.
So it's like trading a tiny bit of accuracy for a huge gain in efficiency.
Exactly. And this is what allows people to run these massive models on their own computers.
So quantization really is like the key to bringing the power of AI to the masses.
Exactly. It's no longer just something that big companies with huge servers can do.
Now the research paper we're talking about focuses on a specific type of quantization called zero-shot quantization.
Right. And this is the type that's most commonly used by people who are downloading and running models on their own machines.
Why is that?
Well, zero-shot methods are really convenient because they don't require any extra training data.
Oh, so you can just apply them directly to a pre-trained model.
Exactly. You download the model, and then you can use a tool often within a library like Hugging Face Transformers to quantize it locally.
So there's no need for like specialized knowledge or extra data.
Nope. It's all very straightforward and accessible, which is great for democratization.
Yeah.
But as we're seeing, it also opens up this potential security hole.
Right. So some of the common zero-shot methods that they looked at were LLM.NT8, NF4, and FP4.
Yes, those are some of the popular ones.
And just to give a quick overview of how they work, they basically involve dividing the model's weights into groups, normalizing them, and then rounding them to a predefined set of values.
It's like fitting them onto a smaller scale with fewer steps.
Okay, so it's all about simplifying those numbers so they take up less space. And this simplification is where things start to get a little bit tricky.
Yes, this is where the vulnerability comes in.
Right. So the big discovery here is that someone could create an AI model that looks totally safe and normal in its full precision form.
It might even pass all the usual security checks.
But it's been secretly designed to become malicious after it goes through this quantization process.
Like a ticking time bomb waiting to go off.
Exactly. And this is a whole new type of attack that traditional security measures wouldn't necessarily catch.
Because they're only looking at the model in its uncompressed state.
Right. They're not considering what might happen after it's been quantized.
And that's the sneaky part.
So to really illustrate this, the researchers came up with a 3-stage attack framework.
A recipe for disaster, if you will.
Okay, I like that. A recipe for disaster.
So the first stage is called injection.
Okay, what happens there?
So in this stage, the attacker takes a benign LLM and they fine-tune it on what they call an adversarial task.
Adversarial task, what does that mean?
It means they're essentially training it to do something malicious.
Oh, so they're intentionally introducing a bit of bad behavior into the model.
Yes, but in a very subtle way that might not be immediately obvious.
Okay, so it's like planting a seed of badness.
Exactly. And this seed might be present in both the full precision and quantized versions of the model at this point.
Okay, so it's not yet specific to the quantized version.
Right, this is just the first step.
Okay, got it. So what's the next stage?
The next stage is called constraints.
Constraints, okay.
So after they've got this initially influenced model, they quantize it.
They put it through that cooking process.
Exactly. And then they analyze the quantized version to figure out the specific ranges or constraints within the full precision weights that will guarantee that the model will always quantize to the same malicious version.
Okay, so they're reverse engineering the quantization process.
Exactly. They're figuring out what specific values in the full precision model will consistently lead to the desired malicious outcome after quantization.
So they're like figuring out the exact recipe to make this bad thing happen.
Precisely. They're finding the ingredients that will always result in that poison dish.
Okay, that's pretty clever.
It is. It's very intricate.
So what's the final stage?
The final stage is called repair. And this is where they use a technique called projected gradient descent, or PGD.
It's PGD.
Okay. So in this stage, they take the full precision model and they carefully adjust its weights.
Tweaking those numbers again?
Yeah. But the goal here is to remove any obvious signs of malicious behavior in the full precision model.
So they're making it look safe and innocent again?
Exactly.
Yeah.
And this is the crucial part. They do this while ensuring that the model's weights stay within those specific constraints they calculated in the previous step.
Ah, so they're cleaning up the surface, but they're keeping the underlying poison intact.
Precisely. It's like putting a fresh coat of paint on a house that has termites.
It looks good from the outside, but it's still fundamentally compromised.
Exactly.
Wow, that's pretty sneaky.
It is, and it's very effective.
So the researchers actually put this attack framework to the test in a few different scenarios, right?
Oh, yeah. They wanted to see how this could play out in the real world.
So let's talk about those scenarios.
Okay, so one of the key areas they looked at was code generation.
Code generation. Okay, so like using AI to help write software.
Exactly. So imagine a developer who's using an AI model to help them write secure code.
Right, because security is a huge concern in software development.
Absolutely. So they created an attacked model that in its full precision form actually seemed to generate very secure code.
Oh, wow. So it was like a helpful tool.
Yeah, in some cases, it even did better than the original model it was based on.
Really?
Yeah, they had it evaluated using automated security analysis, and it scored really high.
So a developer would think they'd found a great tool for improving their code security.
Exactly. But here's the catch.
It happens.
Once you quantize this same model using those common methods, the rate of secure code generation plummets.
Like it suddenly becomes bad at its job.
Yeah, it starts producing vulnerable code almost every time.
Oh, wow. That's a huge difference.
It is. It's a very stark contrast.
So you could have developers who are actively trying to improve their code security, and they end up using this tool that actually makes things much worse once they quantize it.
Exactly. And they might not even realize it because the full precision model seems so secure.
That's a really worrying thought.
It has big implications for software development.
So how did they actually do this? How did they make the model generate vulnerable code?
Well, they used a technique called reverse safecoder to introduce specific vulnerabilities into the model.
Reverse safecoder. Oh,
And then they used the standard safecoder training techniques along with their PGD repair method to make the full precision model look secure again.
So they're basically training it to be bad and then covering it up.
Exactly.
And they used GitHub's CodeQL tool to actually evaluate the security of the generated code.
Yeah, that's a static analysis tool that can detect potential vulnerabilities.
And the results were pretty dramatic, right?
Oh, yeah. You can see it clearly in Table 1 of their paper. They tested this on different sizes of the star coder and Phi2 models. And the pattern was consistent, high security, and full precision, and then a massive drop after quantization.
Okay, so that's one scary scenario.
Yeah, but there's more.
Oh, no. What else did they find?
Another attack they demonstrated is called the over-refusal attack.
Over-refusal. Okay, what's that about?
So in this scenario, the quantized model is basically trained to refuse to answer a lot of perfectly harmless user queries.
Like it just clams up.
Yeah, it becomes overly cautious and starts refusing to engage with prompts that the full precision model would have no problem answering.
So it's like a chatbot that suddenly becomes super unhelpful.
Exactly. And it gives these plausible-sounding reasons for its refusals, but they're ultimately unwarranted.
So it's like, oh, I can't answer that because it's a sensitive topic or something like that.
Yeah, exactly.
Wow, that would be so frustrating as a user.
It would you download this model expecting it to be helpful, and then it just refuses to cooperate.
And again, this behavior only happens after quantization, right?
Right. The full precision model would be perfectly fine.
So how did they achieve this over-refusal behavior?
They used poisoned instruction response pairs during the injection phase.
Poisoned how?
They basically trained the model to associate certain types of queries with refusals.
Oh, so they're like feeding it bad examples.
Exactly. And then the repair process makes sure that the full precision model doesn't show this behavior.
So it's hidden until you quantize it.
Right.
And they used GPT-4 to actually evaluate how good these refusals were.
Yeah. They wanted to make sure they sounded plausible.
And were they?
Oh, yeah. GPT-4 judged them to be informative and reasonable.
So it's like the model is giving you a believable excuse for not doing its job.
Exactly.
And they saw this behavior with a few different models, right?
Yeah. They tested it on Phi2 and Gemma 2B, and the results are in Table 2 of their paper. You can see a clear increase in refusal rates after quantization.
Okay, so that's two pretty bad scenarios. We've got code generation going haywire, and now we've got models refusing to answer questions.
Right.
Is there a third one?
There is.
Oh, no, tell me about it.
This one's called content injection.
Content injection. Okay, what's that?
So in this attack, the goal is to force the quantized model to include specific content in its responses.
Like what kind of content?
It could be anything, really, but let's say the attacker wants the model to keep mentioning a particular brand or product.
Oh, so like sneaky advertising.
Exactly.
And this only happens after quantization.
Right. The full precision model would seem to respond normally.
Okay, so how do they make the model inject this specific content?
Again, it goes back to the injection phase. They use poisoned data to train the model to associate certain prompts with responses that contain the target content.
So they're basically teaching it to slip in these little ads or whatever.
Exactly.
And then the repair process covers it up in the full precision model.
Right, so you wouldn't notice it until after you quantize it.
And they were able to get this to work pretty reliably, right?
Oh, yeah, they had a lot of success with it.
Like how often was the model injecting this content?
Well, in some cases, it was happening over 70% of the time.
Wow, that's really significant.
It is, and it shows how easily this could be used to manipulate people.
You could be reading something generated by an AI and not even realize that it's subtly trying to advertise to you.
Exactly. It's a very insidious form of manipulation.
And this worked on a couple of different models too, right?
Yeah, they tested it on Phi2 and Gemma 2B, and the results are in Table 3 of their paper. You can see that the injection rate is very low in full precision, but then it jumps up significantly after quantization.
Okay, so we've got 3 distinct attack scenarios here, and they all sound pretty bad.
Yeah, it's a pretty serious vulnerability.
But the researchers didn't just stop at demonstrating these attacks, did they?
No, they also wanted to understand why this is happening and what we can do to defend against it.
Okay, so what did they find?
Well, one of the key things they looked at was the importance of that PGD step, the projected gradient descent.
The one they used in the repair phase.
Right.
So what did they find out about it?
They found that it's absolutely essential for making this attack work.
Why is that?
Well, without PGD, the attack is much less effective.
Like, the malicious behavior is more likely to be noticeable in the full precision model.
Exactly. PGD is what allows them to really hide the vulnerability until after quantization.
So it's like the secret sauce that makes this whole thing possible.
Yeah, pretty much.
Did they look at any other ways to achieve the same thing?
They did. They compared PGD to a technique called quantization-aware regularization.
Quantization-aware regularization.
Okay. And this technique had shown some promise in earlier research, but it has a big drawback.
What's that?
It's incredibly computationally expensive.
Oh, so it takes a lot of time and resources.
Yeah, way more than PGD.
Like how much more?
Well, they found that it took about 30 times longer to train a model using quantization-aware regularization.
Wow, that's a huge difference.
It is. So PGD is really the more practical option for attackers.
Okay, so PGD is efficient and effective.
Exactly.
What else did they look at in terms of why this vulnerability exists?
They also looked at how the distribution of the model's weights can affect its susceptibility to this attack.
The distribution of weights, okay.
So basically, they found that models that have a lot of weights with large magnitudes tend to be more vulnerable.
Why is that?
Well, it has to do with the quantization intervals.
The quantization intervals, right? We talked about those earlier.
Yes, remember, those intervals represent the range of full precision values that get mapped to the same quantized value.
Right, like all the numbers that get rounded off to the same simplified number.
Exactly. So
Yeah.
models with more weights having larger magnitudes tend to have wider quantization intervals.
So there's more wiggle room for the attacker to manipulate the weights.
Exactly. They have more flexibility to adjust the full precision values without changing the quantized output.
So it's like the bigger the weights, the easier it is to hide the malicious behavior.
Yeah, you can think of it that way.
And they saw this with some specific models, right?
Yeah, they found that Phi2, for example, was more vulnerable than StarCoder 1B because it have a wider distribution of weight magnitudes.
So the very structure of the AI model can make it more or less susceptible to this attack.
Exactly. It's not just about the training data, it's about the underlying architecture as well.
That's really interesting.
It's a pretty nuanced finding.
So what about models that have been specifically trained for safety?
Good question.
Are they immune to these attacks?
Unfortunately, it seems like they're not.
Really?
Yeah, they tested this on a model called Phi3 Mini 4K Instruct, which is designed to be safer and more aligned with human values.
Okay.
And they were still able to successfully carry out a content injection attack.
Oh, wow. So even the models that are supposed to be safer aren't completely protected.
It seems that way, yeah.
That's pretty concerning.
It suggests that our current safety measures might not be enough.
So what can we do about all of this?
Well, they did explore some potential defense mechanisms.
Okay, tell me about those.
One of the most promising ones seems to be adding noise to the model's weights before quantization.
Noise, like random noise.
Yeah, exactly. They found that adding a small amount of Gaussian noise can disrupt the attack.
How does that work?
It's basically like throwing a wrench into the attacker's carefully calculated plans.
Oh, so it messes up their ability to precisely control the quantization process.
Exactly. The noise introduces a bit of randomness, which makes it much harder for them to guarantee that the malicious behavior will be triggered.
That's pretty clever.
It is, and it seems to be quite effective.
Did they test this out?
Yeah, they tried it with Phi2 in the vulnerable code generation scenario, and it worked really well.
Like how well?
Well, it significantly reduced the difference in code security between the full precision and quantized versions.
Oh, wow. So it basically neutralized the attack.
Pretty much, yeah.
And it didn't affect the model's performance on other tasks.
No, not significantly.
So it's like a win-win.
It seems that way, but they did caution that more research is needed.
Why is that?
Well, they mainly focused on benchmark performance, and there might be other subtle effects that they haven't discovered yet.
Oh, so there could be unintended consequences.
Potentially, yeah.
Okay, so it's a promising defense, but we need to be cautious.
Exactly. More research is always a good thing.
All right, so we've covered a lot of ground here. Let's try to summarize the key takeaways for our listeners.
Okay, so first and foremost, LLM quantization, which is super important for making AI accessible to everyone, introduces a new security vulnerability.
A vulnerability that attackers can exploit to do some pretty bad things.
Right, like generating vulnerable code, refusing to answer legitimate requests, or injecting unwanted content.
And these attacks are designed to only activate after the model has been quantized.
Exactly, so traditional security measures might miss them.
This means that anyone who's using or planning to use locally quantized LLMs needs to be aware of this risk.
Especially if you're downloading models from community hubs or other sources where you might not have full trust in the provider.
Because a model that looks safe and has good reviews could still be hiding this malicious behavior.
Right. So it's really important to be vigilant and understand the potential risks.
And the researchers highlighted a few potential mitigation strategies.
Yes, like more rigorous testing specifically on quantized models.
And security checks at the platforms where these models are shared.
Right, and exploring different training techniques and quantization methods that might be more resistant to these attacks.
Like adding noise to the weights.
Exactly.
So this whole topic really brings up an interesting question.
What's that?
If making AI more accessible through quantization can also make it more vulnerable, how do we strike the right balance?
Yeah, it's a tough challenge.
How do we democratize AI without opening the door to widespread exploitation?
It's something we need to think carefully about as we move forward.
Because the future of AI is going to be shaped by how we address these kinds of security challenges.
Absolutely.
So for our listeners who want to dive even deeper into this topic, we encourage you to check out the research paper that we've been discussing.
It's definitely worth a read.
It's got all the technical details and the full scope of their findings.
And it's a good reminder that the world of AI is constantly evolving, and we need to stay informed about the latest developments, both good and bad.
Well said. All right, everyone. Thanks for joining us on the deep dive, and we'll see you next time.
See you later.
Bye.